Hello and welcome to lecture 58 of the course Computational Complexity. In the previous lecture, we saw Karchmer-Wigderson relation where we could relate the deterministic communication complexity of a certain relation with the depth complexity of a function, right? When it is represented as circuits. In today's lecture, we are going to use the Karchmer-Wigderson relation in order to get a lower bound on the depth complexity of a certain function. The function being given a graph, determining whether the graph has a perfect matching or not. Okay, and this result is by Raz and Wigderson from 1992. So it's a very interesting and somewhat of a surprising application of the communication complexity, right? Because we are getting a depth lower bound on a problem that is on graphs, right? So before we start, let me just recall monotone functions and monotone circuits. So monotone functions are those where if there are two inputs x and y, if x is greater than or equal to y, then f of x is greater than or equal to y. So remember, all of this is in the Boolean function. So n bits to 0, 1 output. Okay. And when I say x is greater than or equal to y, I mean bitwise. So the function, the output of 0, 1, 1, 0, 1 should always be greater than 0, 0, 1, 0, 1, 1, because here x is greater than y, so f of x should be greater than or equal to f of y. Another way to view the same thing is that if you change an input bit, one input bit from if you flip it from 0 to 1, then the output cannot go from 1 to 0. The output cannot decrease. The output may remain same at 0 or 1. The output may increase from 0 to 1, but it cannot go from 1 to 0. Right? This is another way to view monotone functions. And monotone circuits are just whatever we can implement with just and OR gates. Okay, and in fact, we had seen these definitions in lecture 35. In fact, there was also an exercise where I had asked you to verify that a function f is a monotone function if and only if it can be implemented by a monotone circuit. Okay, so hopefully, if you have not convinced yourself of this simple fact already, you may want to try that out and then listen to the rest of the lecture. Okay. So the point here is that any function, if it is a monotone function, then it can be implemented by a monotone circuit, and anything that can be implemented in a monotone circuit is a monotone function. Okay, so it's an equivalent characterization. So given a function, given a monotone function, right, I can ask what is this, like I can construct given a monotone function, I can construct circuits that implement this, circuit families, right? And I can look at the depths of these circuits. Now what I am further restricting it is, so this is the depth of the function. What I am further restricting it into is the monotone depth, denoted by d superscript m of f. Okay, so this is the monotone depth. This means you restrict yourself to only the monotone circuit characterizations of f, or monotone circuit realizations of f. Okay, so even if f is monotone, perhaps you could have a very compact circuit using NOT gates, okay, using negations and some things like that. And perhaps when you try to implement it using a monotone circuit alone without using NOT gates, perhaps the size increases, right? So the monotone depth could be more than the depth of the function, right? Because I am only looking at functions or circuit implementations that do not have NOT gates, right? So d superscript m of f, this stands for the depth of the monotone circuits that implement f. So this is the monotone depth. Okay, so this is the monotone depth of a certain function, which is the depth using monotone circuits. And last lecture we defined the Karchmer-Wigderson relation, which was xyi, such that xi and yi are different, right? So let me just go to the previous lecture and show you what it was. So Korchmar-Wigderson relation was set of all xyi such that xi is not equal to yi. And here we are defining the monotone Korchmar-Wigderson relation. So everything is same except that in the case of Korchmar-Wigderson relation, we said that xi not equal to yi. In the monotone variant, we say xi equal to 1 and yi equal to 0. So I am telling xi should be 1 and yi should be 0. And we cannot have xi not equal to yi in general, right? So we cannot have xi equal to 0 and yi equal to 1. Okay, so this is a monotone Korchmar-Wigderson relation. Okay, and just like what we saw in the last lecture, we can also define the monotone variant of the Korchmar-Wigderson theorem, which is that the monotone depth of a certain function is equal to the deterministic communication complexity of the monotone Korchmar-Wigderson relation. So it's exactly the same theorem, but for the subscripts m in the left hand as well as the right hand side. So you can work out the proof. It is exactly along the same lines, but then you just have to take care of the fact that the depth is of a monotone circuit, and so which means in the case of monotone circuits, as I explained in the previous lecture, all the negations, all the inputs are in the positive form. So I won't have inputs of the form Zi complement, Z2 complement, and so on. It will all be Z1, Z2, Z3, and so on. Okay. So the monotone the monotone depth is equal to the communication complexity of the monotone Korchmar-Wigderson relation, right? So this you can try out. Okay, so now let me come to the main topic. So given a graph, so you can think of giving a graph as an adjacency list or adjacency matrix, right? So I can view a graph as a big vector. So for instance, here I have a graph on 4 vertices. Let me number these vertices. Let's say 1, 2, 3, 4, right? So now I could represent this graph as a 6-bit vector, right? So I would say, so it's a simple graph. So let me represent it as a 6-bit vector. So the first bit indicates whether there's an edge from 1 to 2, then second bit indicates edge from 1 to 3, 1 to 4, 2 to 3, 2 to 4, and finally 3 to 4. So for this graph, it will be 1 to 2 there is an edge, 1 to 3 and 1 to 4 there are no edges, so we put 0, 0, 2 to 3 there is an edge, 2 to 4 there is an edge, 3 to 4 there is an edge. So this is the vector that indicates this graph. Okay. So now the question is, given this n choose 2-bit vector, which is an entire description of the graph. So there are no self loops, assume there are no self loops, an undirected graph. So edge from I to j is the same as edge from j to I, and no self loops. So given this vector, one has to determine whether there is a perfect matching. So you can check this graph. Does it have a perfect matching? Yes, indeed it does. So you could pick the edge 1 to 2 and maybe the edge 3 to 4. In fact, this is the only perfect matching, right? But let's say if I had a couple of more edges, let's say right, 5 and 6. Now does this graph have a perfect matching? Okay, even this does, because you could consider something like this, right? This is a perfect matching. In fact, I think this is the only perfect matching of this graph. But if it was, let's say, if we did not have this edge 2, 4, then we don't have a perfect matching, right? Because 5 has to match with 1 and 6 has to match with 3. So 2 and 4 do not have pairs, right? Okay, so this for the vector of this particular graph, there is no perfect matching. So the match n function is just given this vector n choose 2 long vector. It will map to 0, 1 depending on whether the graph has a perfect matching or no perfect matching. Okay, so now let us move to the theorem by Raz and Wigderson, which is a lower bound on the depth complexity of this function. Okay, This says that the depth complexity of this matching function is at least linear. Right? The depth complexity of the matching function is at least linear. You have to have a linear depth circuit to compute this. So you may recall that we saw an RNC circuit to determine whether the given bipartite graph has a perfect matching. But in RNC circuit, it's like polylog depth circuit, right? But here we are saying that if we restrict the circuit to a monotone circuit, right? Again, that was RNC, but here it is monotone circuit and deterministic. Then the circuit has to be of depth, linear depth. Okay. So we will. This is proved via the Karchmer-Wigderson relation. Okay. So given the matching function, what is the corresponding Karchmer-Wigderson relation? So one way to think of it is that Alice and Bob get vectors. Alice has a vector which outputs 1. So which means he has a graph. So this vector is a representation of a graph. Alice, she has a graph that has a perfect matching because the matching function evaluates to 1. Right? And Bob has a graph that does not have a perfect matching. Right? So the matching function evaluates to 0. So this means that Alice must have an edge that is not there with Bob. Right? Because matching is a monotone function. If you put an additional edge, the perfect matching that was already there does not vanish. Right? So Alice has a perfect matching, Bob does not have a perfect matching. So they have to determine one specific edge that Alice has and Bob does not. This is a requirement. Right? Alice and Bob needs to determine that one edge that is in Alice's graph but not in Bob's graph. So this is the requirement of the function. We will show that the disjoinous function, right? So the disjoinous function, we already said that it is you require at least n bits. We will show that there is a randomized reduction from the disjoinous function to this relation, this Karchmer-Wigderson relation on matching. So you can reduce the disjoinous function in a randomized fashion to this Karchmer-Wigderson relation. So if there is a Karchmer-Wigderson, if the relation, a protocol for the Karchmer-Wigderson relation on matching, right, will correspond to a randomized protocol for disjoinous, because given a disjoinous instance, we transform it to a matching instance or an instance of computing the Karchmer-Wigderson relation. Okay, so this transformation is randomized, and then run the protocol for the Karchmer-Wigderson relation on matching. Right? We run the protocol on R match, and then using that we will be able to determine whether the inputs were disjoint or not. So it's a randomized process to decide disjointness, randomized protocol to decide disjointness. Right? And the interesting thing is that this will involve no extra communication. Whatever this reduction entails, this will be done locally at Alice's end and Bob's end. They will not need to communicate with each other to perform this reduction. So the communication complexity of the resulting randomized protocol for disjointness will be exactly the same as the communication complexity of the protocol that decides the Karchmer-Wigderson relation or that computes the Karchmer-Wigderson relation. Right? So this gives us a randomized protocol for disjointness. But then there is a result which I will not prove, I will just state, that states that the randomized complexity of disjointness is at least linear. Okay, so this was a result in 1992 by Kalyansundaram and Schnitger, who showed that the randomized complexity of disjointness is at least linear. And here we have a randomized, via this reduction from to the Karchmer-Wigderson relation, we have a randomized protocol for disjointness, right, without any extra communication complexity. So this means that since we know that randomized complexity of disjointness is at least order n, at least omega n, this means that the complexity of R match is also at least order n, right? This means the complexity of R match is also at least order n. And by the Karchmer-Wigderson theorem in the monotone setting, this means that because the deterministic complexity of R match is equal to the monotone depth of matching as well. So this implies that the depth complexity of the matching circuit that computes matching in the monotone setting is also linear. So that is the overview of the proof. Once again, I'll just quickly go through. We reduce disjointness in a randomized fashion to the R match being the Kurzweil-Wigderson relation on matching. So a protocol for R match gives a randomized protocol for disjointness with the same complexity because it involves no extra communication. But we know that randomized complexity of disjointness is at least linear. So the protocol for R match should also be at least linear. But by the Kurzweil-Wigderson theorem, we know that the complexity of the protocol for R match is equal to the depth complexity of the function. So the depth complexity, the monotone depth complexity of the matching function is also at least linear. Right. So now what remains is to see the reduction. Right. This particular reduction. Right. This particular reduction is what is left. Okay. So in fact, we'll present a slightly simpler reduction, but it's not very difficult to see the idea from this, right? So the core idea I will just present in reduction. So instead of asking whether a n vertex graph has a perfect matching, we'll ask whether a graph with 3n plus 2 vertices has a matching of size n plus 1. Okay, so a graph with 3n plus 2 vertices has a matching of size n plus 1. Okay, so how will the reduction happen? So Alice and Bob get 2 strings of length n. Okay, 2 strings of length n, and they will construct matching instances locally. Okay, so but they will construct different graphs, and that will help us do the reduce disjointness to this matching function. Both of them will construct graphs on 3n plus 2 vertices. Okay, and their construction will be dependent on the strings that they have. So the 3n plus 2 vertex graph looks like this. So the 3n plus 2 vertices are in this form. For each, so let's say n is equal to 4, then we have 4 such n tuples, or 4 such 3 tuples, sorry. This is 1, this is 1, this is 1, and this is 1. Right? 4 such 3 tuples, a1, b1, c1, a2, b2, c2, a3, b3, c3, and a4, b4, c4. So that corresponds to 3n, and then there is a single edge, or there are 2 vertices called d1 and d2. Okay, that is there by the right side. 2 vertices called d1 and d2. Okay, so this is the 3n plus 2 vertices. Now what are the edges? So let me first describe. So the vertices are common to the graphs of both Alice and Bob. The vertices are common, only the edges will differ. So let us see what is the graph, Alice's graph, let us call it GA. Okay, so let us look at this Alice's string. Let's say the string is 0, 1, 0, 1. So the first bit is 0, so you xi equal to 0 means I'll just erase some of this. Xi equal to 0 means add edge between AI and BI. So you make AI and BI adjacent. Xi equal to 1 mean you add an edge between BI and CI, and that's it. So Alice's graph, and finally also add edge. This you always add for Alice, D1 and D2. So Alice's graph has exactly n plus 1 edges, right? So there are n plus 1 edges. For each bit, whether it is 0 or 1, she adds an edge between either AI and BI or BI and CI. And finally, there is an edge between D1 and D2. Okay. So this is the graph. This is the graph of Alice. It is just. So in fact, the graph itself is just a perfect matching. There is no other things going on here. A lot of vertices without any edges. Okay. This is Alice's graph. So x is 0, 1, 0, 1. So you connect A1 and B1, but second bit is 1, so you connect B2 and C2. third bit is 0, so you connect A3 and B3, fourth bit is 1, you connect B4 and C4, and finally you connect D1 and D2. Now let's see Bob's graph. So again it's on the same set of vertices, A1, B1, C1, A2, B2, C2 and so on, right? So same set of vertices. We call this graph GB, okay? And what are the edges? So what we do is we have these universal vertices. So what do universal vertices mean? So we mark B1 as universal. So what we do is you have an edge from B1 to A1, C1, B2, A2, everything. So to all the vertices. So you make B1, so this notation where I have a red circle, these vertices are made universal, meaning you make them adjacent to all the remaining vertices of the graph. So even including D1, right? D1, D2, everything. Okay. And which vertices are made universal? Yi equal to 0 means you make Bi universal, and Yi equal to 1 you make Ai universal. So in every group, every 3 tuple or A1, B1, C1, Ai, Bi, Ci group, you make one vertex universal depending on what the ith bit is. So you can see the string is 0, 1, 1, 0. So since the first bit is 0, B1 is made universal, second bit is 0, so A2 is made universal, second bit is 1, so A2 is made universal, third bit is 1, A3 is made universal, fourth bit is 0, so B4 is made universal. So because it will get messy, I am not drawing all the edges, because a universal vertex means it's connecting to all the remaining edges, the 3n plus 2 vertices. So a universal vertex results in 3n plus 1 edges, right? So many edges, it will just get messy. So there are 4 such universal vertices. And this is the graph GB, Bob's graph. Okay, what I want to mention here is, look at Alice's string and Bob's string. The claim is this. So notice that Alice's graph has a matching of size n plus 1. In fact, it is just a matching of size n plus 1. What can we say about Bob's graph? We know that any edge in Bob's graph, one of the endpoints is the universal vertices. So for instance, there will not be an edge between A4 and C4 because neither vertex is universal, right? So this edge will not be there, A4 and C4 will not be there. So, and how many universal vertices are there? There are overall n universal vertices. So any edge has one of these n universal vertices as its endpoint. There could be edges that have both of them as universal vertices as endpoints, but that's okay. Every edge has at least one of its endpoints as a universal vertex. This means that you cannot have a matching of size bigger than n, because if you have a matching of size bigger than n, that means you have let's say n plus 1 edges. That means you have n plus 1 edges, and each one of them should have one of the universal vertices as its endpoints, and you cannot share an endpoint. But then you have only n universal vertices. So any matching in graph B, Bob's graph GB, has size at most n, and GA has a matching of size n plus 1. In fact, it is a matching. GA itself is just a matching. There is nothing else. But any matching in GB is of size at most n. So now Alice's graph has now, by construction, it is a yes instance, and Bob's graph is a no instance. So the matching function applied to Alice's graph outputs 1, and applied to Bob's graph outputs 0, right? Because now we are trying to determine whether is there a matching of size n plus 1, right? That's what we said we'll do a simpler reduction. Okay, so now I want to point out something about the way these things were constructed. So the point is that if x and y are disjoint, meaning there is no index where both xi and yi are 1, then what happens is that there are three possibilities: xi equal to 0 and yi equal to 0, xi equal to 1, yi equal to 0, xi equal to 0, yi equal to 1. In each of these cases, the universal vertex of that group I is an endpoint of the edge added by Alice. So let us see. So in fact, in this figure, all possibilities are covered. So for the first group, x1 equal to 0 and y1 equal to 0. So the universal vertex is b1, and that is an endpoint of Alice's edge a1, b1. For the second bit, x2 equal to 1 and y2 equal to 1. So it is not disjoint. But let's see what happens. The universal vertex is a2, but a2 is not an endpoint of b2, c2, which is the edge added by Alice. In both the third group and fourth group, Alice and Bob are disjoint. Alice has 0 and Bob has 1 for the third index. Alice has 1 and Bob has 0 for the fourth index. And you can see that in the third group, a3 covers a3, b3, and in the fourth group, b4 covers b4, c4. So any possibility, if x and y are disjoint, then all the endpoints of Alice's graph are covered by Bob's graph. Okay, so what I mean is that if Alice and Bob are disjoint, then all the edges added in a1, b1, a2, b2, c2, a2, a1, a2, b2, whatever, all these groups, all the edges added in these groups, a1, b1, c1, a2, b2, c2, are covered by the universal vertices added in Bob's graph. The only edge in Alice's graph that will not be covered is the edge d1, d2, because Bob is not going to add a universal vertex in d1 or d2. Okay, so this is the key observation. So I've just written down that here. If x and y are disjoint, the universal vertices in GB cover Alice's edges. Okay, so this is the key point. It covers Alice's edges. If x and y are not disjoint, then there is at least one edge in Alice's graph, right? At least one edge that is not covered by a universal vertex in GB. Okay. So if x and y are disjoint, then the universal vertices in GB cover Alice's edges. In fact, this one more point, except d1, d2. It covers all the edges except d1, d2. But if they are not disjoint, then there is an edge apart from d1, d2, right? Apart from d1, d2, that is not covered by the universal vertex in GB. And if this point is clear, the rest of the proof is very, very straightforward. So all that now it boils down to is that if it is disjoint, the only edge that Alice has, but that is not there in Bob's graph, is d1, d2. So if Alice and Bob are disjoint, the only edge that Alice's graph has, but Bob's graph does not have, is d1, d2. If they are not disjoint, then there are multiple edges that Alice has that Bob does not have, including d1, d2. At least one more edge apart from d1, d2 is there with Alice. Okay, so a correct execution of correct computation of the Kaczmar-Wigderson the protocol of the Kaczmar-Wigderson relation on matching should output an edge from Alice's graph. So if Alice's and Bob's input are disjoint, then it will always output d1, d2, because everything else is already covered by Bob's graph. If they are not disjoint, then it could be D1, D2 or it could be some other edge, and that is a key thing. So what is the protocol? Alice and Bob build their graphs G1, GA and GB, and there is one small step that they do. This is to remove any bias of the algorithm. So you can come think about it later. That what they do is, using shared randomness, they permute their vertices and edges, okay, with the same permutation. So this is, just think of it as just relabeling. This is to make sure that the protocol does not have any bias towards looking at some set of edges versus some other set of edges. Okay, but both of them do the same permutation. So if Alice relabels A1 to X and B1 to Y, then Bob also will make the same relabeling. Okay, so if their inputs are disjoint, if Alice's and Bob's inputs were disjoint, then the protocol must output D1, D2. If they are not disjoint, then there are other edges, at least one other edge that Alice can output, right? So the probability that D1, but even D1, D2 can be output. So what is the probability that D1, D2 can be output? It is at most half, because there is at least one more edge, right? And this probability that of outputting D1, D2, this can be further reduced by boosting. You could repeat that. So now all that they need to do to distinguish whether X and Y are disjoint, right? So again, recollect that we are trying to reduce disjointness to a computation of the Karsmer-Wigderson relation. So they will compute the Karsmer-Wigderson relation, which means they will arrive at an edge that Alice has that Bob does not have. They will look at the edge. If this edge is D1, D2, they will say that the strings are disjoint. If this is not D1, D2, they will say that the string is are not disjoint. X and Y are not disjoint. And we can improve this probability by boosting, by repeating and boosting. So the bottom line is that we can distinguish the case when disjointness is 0 and disjointness is 1 by using this protocol. Right? It's a random protocol because we do this random permutation. So we transform X and Y into graphs, and if they are disjoint, the only output possible by Alice and Bob is D1, D2. Otherwise, there are multiple outputs possible. So if Alice outputs some other edge, like in this case, she may output B2, C2 because they are not disjoint, right? Then they know that Alice and Bob know that the strings are not disjoint. So what is the conclusion? The conclusion is that we are computing disjointness using the Karsmer-Wigderson relation on matching. Right? We are computing disjointness using the Karsmer-Wigderson relation on matching. This means that the complexity of disjointness is at least the complexity of the Karsmer-Wigderson, computing the Karsmer-Wigderson relation on matching is at least that of the randomized complexity of disjointness, which we know to be at least linear. So that gives us that complexity of R match is at least linear, and by the relation between the complexity of R match and the depth of the matching, we know that the depth of matching is also linear, the monotone depth of matching. So that completes the proof. I'll just do a quick recap, right? So we first saw monotone functions and monotone circuits. Again, this was a recap. And then we said that the Karsmer-Wigderson theorem that we saw in the previous lecture has a monotone analog. The monotone depth complexity is equal to the deterministic complexity of the monotone Karsmer-Wigderson relation. And then we defined the matching function, right? And then we saw that R match, which is the Karsmer-Wigderson relation applied to the matching function, can be reduced, or from disjointness there is a randomized reduction to R match. So a protocol for R match will give a randomized protocol for disjointness without extra communication, right? And since the randomized complexity of disjointness is at least linear, this implies that the deterministic complexity of R match is at least linear, and hence the depth complexity, the monotone depth complexity of matching is also linear. And the reduction was just a simple graph. Alice's graph was just a matching of n plus 1 edges, and Bob's graph is just a bunch of universal vertices. So by construction, we ensured that Bob's graph does not have a matching of size n plus 1, and Alice's graph has a size of matching of size n plus 1. And the key thing was that if the strings were disjoint, then Alice will always output D1, D2. If the strings were not disjoint, then Alice could potentially output other things, or Alice is sure to be able to output at least one more string or one more edge. Alice has other option. So the probability of outputting D1, D2 is at most half, and which could be further improved by boosting. And the protocol is, if Alice and Bob output D1, D2, then say it is disjoint. If they don't output D1, D2 and output something else, say it is not disjoint. And that completes the summary of this proof, that monotone depth complexity of matching is at least linear. Just to summarize what we saw this week, we saw communication complexity. What is communication complexity? The communication complexity model. Then we saw a bunch of techniques. We saw the protocol tree, we saw the matrix, we saw lower bound techniques such as the tree in the bound on the number of monochromatic rectangles. Then we saw fooling set. Then we saw size based bound. We saw size based bound, right? And we saw fooling set, size based bound, and then we saw rank bound, and then we stated the log rank conjecture, right? We didn't prove the rank bound, and then we saw this connection between circuit complexity, depth complexity, and communication complexity by the Raz-Wigderson theorem, and then we saw this application into for matching that computes the lower bound for matching in this lecture. And that completes the part about communication complexity and also completes week 11. So that's all. Thank you.